All right, let me talk to you today a little bit about, first of all, about vector fields. A vector field in 2 dimensions or be extended 3 dimensions or beyond, I guess, but it's a function that f, denote this way, f with the vector symbol on it there, or in most books it'll be boldface. But anyway, it's a vector. It's a function that assigns each point xy to a 2-dimensional vector, and so each so it's a vector field. It's a function that assigns each xy x comma y a 2-dimensional vector. As far as graphically speaking, if you've seen a wind chart on the Weather Channel or something like that, you've seen an example of a vector field, and we'll draw one here in just a second. There's some notation. So we've got a function, and the function we plug in 2 dimensions an x comma y, and that assigns it a vector, each one of those. And so you've got a function for your I component, p, call it p, and then a function for your j component, call it q. Then if you have three dimensions, x, y, and z, and it's p, x, y, z, I, q, x, y, z, j, and then r, x, y, z, k would be the assignment we'd give for it. Okay? And these functions that are the component parts, those are called scalars. P, Q, and R are called scalar functions for our vector function here. Just a little more terminology there. Okay. So yeah, it gets quite fun to sketch one of these by hand, because it's each point gets a vector. So let's do one just to see how this is going to work. All right, so let's sketch fxy equals 1/2 y, the I component minus xj. Okay, so if we do a little table here, maybe a long table. All right, so we've got xy, and then over here we'll put our f of xy values. So yeah, if you're thinking about those wind charts, wind tables, or whatever you want to call them, what you kind of see is kind of what's happening, as you get further and further out, kind of in a circular way. And so we just mark off units here. And let's just start where we want, but let's go around the circle here at 1, 0, 0, 1, and -1, 0, 0, -1. to start with, just see what we've got. All right, so 1, 0, what we do is we assign the I component is going to be 1/2 y, so that'd just be 0. And then the j component is negative x, so that'd be negative 1. And so at 1, 0 right here, we need to draw in the vector 0, negative 1. And so that would just be nothing in the x and then down 1 in the y. So that would be that vector. All right, then if we have the point 0, 1, 1/2 of y would be 1/2, and then negative x would be 0. Let's go ahead and do these so we can do them a couple at a time. So this would be at negative 1, 0, we'd be at half y would be 0, and then negative of negative 1 would be positive 1. And then at 0, negative 1, we'd have 1/2 y would be negative 1/2, and negative x would be 0. So if we draw those in at 0, 1, we are at 1/2, 0, and so that vector would be that. At negative 1, 0, we're doing the 0, 1 vector, so that would be like this. And then at 0, negative 1, we are at negative 1/2, 0, so that would be back like that. Okay? And so you just kind of want to spread out or go, I guess we could get some in here, but let's work on some just kind of going out. Kind of looks like a maybe a 1, 1 point would be a good one. What have we got going? And then maybe 2, 0. Let's try 0, 2. Back here. How about let's look at negative 1, 2. See what that does for us. All right, so that's 1, 1, so that'd be 1/2, negative 1, be the vector. 2, 0 would be 0, negative 2. 0, 2 would be positive 1, 0. And then negative 1, 2 would be 1, 1. Did those right? Okay, so 1, 1. So at 1, 1, drawing the vector 1/2, negative 1. So 1/2 for the x and then down 1, so that's going to be here. 2, 0, which is here. Looking at 0, negative 2, so that's a little bit longer vector. And then 0, 2, right here. We're at 1, 0. And then at negative 1, 2, we are at 1 and 1. So up 1, over 1. Okay, so you kind of get the feel. I did a couple more at, let's see, 2, 2. Turns out the vector looks like that. At negative 1, 2, wind up getting something like that. At 0, negative 2, it's that vector. At negative 1, negative 1, get this vector at negative 2, 0. You can check all those just to be sure, but okay, so yeah, you kind of get this kind of a wind chart that you can kind of see that, yeah, as you go further out, of course the vectors are getting longer, further out from 0, 0 that you go. So anyway, it's a fun little exercise that you know, you just keep piling on points and see what you get. All right. Now, if you'll recall, we've already kind of talked about vector fields. We just didn't call it that before. If you recall, our gradient vector, let's recall the gradient vector. For f of x, y, z, let's just do three dimensions here. And of course, the two-dimensional is very analogous. The gradient of f, remember what it was? Well, it was the vector composed of the partial derivatives. F, the partial derivative with respect to x, partial derivative of f with respect to y, partial of f with respect to z. Well, in what we're talking about today, we can just consider this now a vector field. And we can graph our little components there, point by point by point. So yeah, this now we can consider it a gradient vector field. Where for each point x, y, z, then the values for our vector field are made up of the partial derivatives. Okay, so for example, let's find the gradient vector field for and we'll just do two dimensions. F of xy equals x squared plus y squared. Easy enough. The gradient vector field would just be our partial of f with respect to x, comma the partial of f with respect to y, or put it in the ij form if you want to, but this is what it is, so easy enough. Partial with respect to x would be 2x. Partial with respect to y would be 2y. Okay? Now, talk about here let's talk about the graph here. Let's graph the gradient vector field along with some contour maps. And remember there, those, what we mean by that is we take f of xy equals some constant k, and then just see what the graph of those look like. And the ones I'm going to show you, I've already done this, so I want to make a quick point or two here. Let's do it for k equals 1.5, 3, 4.5, going by increments of 1.5, and all the way up to 13.5. All right, and so here is our result. The result looks like this. All right, so you can see that, yeah, the first one, the inner circle there is at 1.5. So x squared plus y squared equals 1.5. Of course, the rate, these are just going to be circles. Obviously, the contours are, where your radius is the square root of whatever k is. And then, now, on this particular thing I generated with Mathematica, our vectors there, notice they're they incrementally get larger. I think these are multiplied or divided by some multiple there. But anyway, what you can see, what are a couple things you notice there? What we can notice there is that our vectors are all running perpendicular to the contours. And that will always be the case for the gradient vector field with the contour map of our function. The vectors of the gradient vector field are perpendicular or orthogonal always to the contours. Contour maps. What else do you notice? Well, as our, I set these in increments of 1.5 here, the contour maps. Well, if you'll notice that as the rings get closer together, what happens to the vectors? Well, the vectors themselves are getting a larger magnitude, proportionally so, right? The closer the rings are, the larger. Well, this is explained by looking at this map right here. Huh? Yeah. I'm looking at it on the computer here. So. All right, so yeah, what we've got here is this the contour map of f of xy equals x squared plus y squared, the little rings, and k equals 1.5, 3, so I'm incrementally spaced out by 1.5 there. And then we're looking at the gradient vectors, which we're calling a vector field, and got those drawn out there, or printed out, okay, shown on the figure there. So anyway, what we see is that, yeah, as the contours, as we progress out, k gets larger and larger, the contours get closer and closer together. What does that mean? Well, that means the graph's changing much more than it is when you're at the smaller values for k there. So as you progress further out from the origin, the rings get closer together, so that means you've got more change in your graph. It's changing a lot quicker there. But the vectors are also larger, which also means that since this is the gradient vector, that's our derivative. So doesn't that also mean the change is getting greater? Yeah. And so the two kind of mix together there. They show the same thing. Closer contours means more change, quicker change, and so does the vector field. The larger the vector, the greater the change. So anyway, just point that out. Okay? All right, now, one other point on this section here. And that is, they go ahead and define here what it means for a vector field to be conservative. A vector field is conservative if there exists a function f such that so our vector field is, again, the notation is f, big F, vector, such that the vector equals the gradient of function f. So vector field is conservative if there exists a function f such that f is a gradient of this function little f, okay? And if that's true, little f is called the potential function for big F. Yeah, so basically what this is saying is big F here, vector f, is conservative if it's a gradient of some other function, or of some function. It's a gradient vector field of some function. Just to give you an example, and we'll talk about this more later on, but let's say we've got vector field equals y is the I component plus x is the j component. All right, so that's our vector field. Okay, so this is conservative. With potential function f of xy equals xy, since if you look at the gradient of f, what do we got? Gradient of f, remember that's the partial with respect to x. Partial with respect to x of that would be y. Partial with respect to y would be x. Isn't that what our original function was here? Our original function vector is? Okay. Yeah. Those are equal. So it's that one's a conservative one. Now, f equals negative yi plus xj is not conservative. I think it's pretty, with that example there we have, might be pretty easy to see that this one's not conservative. Since there is no such that f, the gradient of f equals big F, vector field function. You can kind of maybe see that, because if I tried to get negative y out of that same function, that would probably mean including a negative in front of it, but that would also make the x, the partial with respect to, so this, we can get the partial with respect to x negative y, just add a negative there, but that would make the partial of y with respect to, partial of f with respect to y would be negative x, yeah. So it's going to be tough to get that one, you see. But anyway, so there are conservative ones and not conservative ones. Just be aware, okay?